In this video, I'll talk about the coefficient of determination, or R-squared, for multiple linear regression. So we're going to use the same example we used in the last video. So it's a trucking company with miles and deliveries are our predictors, and then time is our response. So we've fit this model previously and come up with these three estimates: minus 0.869 for the intercept, 0.06113 for the coefficient that multiplies miles, and 0.93 for the coefficient that multiplies deliveries. And then we talked briefly about this analysis of variance table. So the analysis of variance table has a column for the sums of squares, which is what SS stands for, so sums of squares in this column. And there's a sum of squares for regression, which comes to 21.6006 in this case. Sum of squares for error, 2.2994, and then a total sum of squares, which is the sum of these two things. And if we take the ratio of the regression sum of squares to the total sum of squares, that's what R-squared is measuring. And for multiple linear regression, we would interpret this number, often turn it into a percentage first, so 90.38%, and we would say we can explain 90.38% of the variation in the y variable about its mean by using this multiple linear regression model that has x1 miles and x2 deliveries as the predictors. So one thing to be careful of here is we're using the word explain, but we're not implying any causality here. All we're doing is demonstrating an association between y and x1 and x2. And we're saying when we build that association using this equation, then we can explain 90.38% of the variation in y using that equation. So there's also something called adjusted R-squared. So the regular coefficient of determination is just called R-squared, but there's an adjusted version. And the formula for that is given here. And it's based on the regular R-squared, but it also takes account of this 2 in the formula here is the number of predictors in the model. So because the number of predictors in the model is used to adjust R-squared, then this is actually a good criteria for comparing different models. So for example, if I had another predictor, an x3, and I fit that model, and I was to calculate R-squared for that model with another predictor x3, the R-squared for that model would necessarily be at least as big as 0.9038. More likely it would be bigger than that. If I added an x4, it would be bigger still. So R-squared just keeps increasing whenever I add predictors, even if those predictors really have very little to do with the response. And so that's why analysts like to look at adjusted R-squared when comparing models like that, because adjusted R-squared accounts for the fact that you're adding predictors, and so adjusted R-squared will only increase if the predictor you're adding is actually somewhat useful in modeling y. So by itself, just like this, looking at this number, it's not very meaningful, 0.8763. But as I say, if we were to do some model comparison, then we would compare the adjusted R-squared for the different models, and we would favor the model with the highest value of adjusted R-squared. So that's what this number is here, adjusted R-squared. So let's fit this model in Excel stat again. and then see if we can find R-squared and adjusted R-squared in the output. Because ordinarily we wouldn't really want to calculate these things by hand. We would just like to be able to fit the model and then locate the two relevant numbers in the output. So that's what we'll do here. Oh, that's a little too big. There we go, that's better. Okay, so what are we looking for? We're looking for R-squared of 0.9038 and adjusted R-squared of 0.8763. Let's see if we can find those numbers. So they're in this table that ExcelStat calls goodness of fit. And there's R-squared. Actually, let me add a decimal place there, see if it matches what we got. Yeah, and I'll add a decimal place there too. So yeah, so there's the two numbers that we just looked at, R-squared 0.9038. So that tells us 90.38% of the variation in Y can be explained using this multiple linear regression model, and then adjusted R-squared, which in and of itself isn't a very interesting number, but if we were to do some model comparisons, this number would play a role in those comparisons. Okay, so that's all about the coefficient of determination, or R-squared, in multiple linear regression.